Hey there, welcome to Lab Partner 101, your study buddy for making science and math simple. I'll walk you through tough concepts step by step so you never feel lost. Let's dive in. What if the universe isn't just full of moving galaxies, but the fabric of space itself is stretching right now? In this lesson, we'll walk through how we know the universe is expanding, what that means, and what it reveals about the cosmos. Curious? Hit subscribe and let's keep exploring together. Let's start with a simple question. Is the universe static or changing? For most of human history, the assumption was that the universe had always been as it is now, unchanging, infinite, eternal. Even Albert Einstein initially assumed a static cosmos when he published his equations of general relativity in 1915. To maintain that stillness, he introduced a cosmological constant to prevent the universe from collapsing under gravity. But the math didn't lie. His equations actually predicted a dynamic universe, one that could expand or contract. What does expansion actually mean? Imagine space as a stretchy fabric. Galaxies aren't flying through space like projectiles. They're being carried with space as it stretches. The distance between galaxies grows, not because they're moving, but because space itself is expanding. This expansion only matters at large scales. Within galaxies, or even galaxy clusters, gravity dominates and keeps things bound. But on scales of hundreds of millions of light years, expansion takes over. Think of raisins in bread dough. As the dough rises, the raisins get farther apart, not because the raisins move, but because the dough expands. So how do we know space is expanding? Light holds the clue. When a wave stretches, its wavelength increases. For light, this means shifting toward the red end of the spectrum, what we call redshift. This effect was first observed in galaxies by Vesto Slipher in the 1910s, and later analyzed by Edwin Hubble in the 1920s. Hubble measured distances to galaxies and found a clear trend. The farther away a galaxy is, the more redshifted its light. Let's quantify redshift. We use the formula Z equals the difference between lambda observed and lambda emitted, divided by lambda emitted, where Z is the cosmological redshift, lambda represents wavelength, the length of one full wave cycle. Wavelengths of visible light are often measured in nanometers. 1 nanometer is 1/billionth of a meter, or 1 times 10 to the negative 9 meters. Angstroms. 1 angstrom is 1/10 billionth of a meter, or 1 times 10 to the negative 10 meters. To put that in context, violet light has wavelengths around 400 nanometers, red light around 700 nanometers. In angstroms, that's 4,000 to 7,000 angstroms. So when a galaxy's light shifts from 400 to 440 nanometers, it's not a small change. It's evidence of the expanding universe stretching space itself. A higher redshift means the light has been stretched more, meaning the source is farther away and moving faster relative to us. This led to Hubble's law, V equals h0 times d, where v is velocity. The galaxy appears to recede in kilometers per second. D is distance, in megaparsecs or MPC. h0 is the Hubble constant, today estimated around 70 kilometers per second per megaparsec. The data showed that galaxies aren't moving through space. Space itself is expanding and taking everything with it. This realization shattered the idea of a static cosmos and paved the way for the next big question. If everything is moving apart now, what did the universe look like in the past? Rewind the expansion far enough, and you reach a time when the universe was incredibly hot, dense, and compact. That moment marks the beginning of the Big Bang model. Let's clarify. The Big Bang wasn't an explosion in space. It was the expansion of space itself, from a much denser state, roughly 13.8 billion years ago. In the early seconds after the Big Bang, the universe was a high-energy soup of quarks, gluons, and radiation. Within minutes, temperatures cooled enough for nuclear fusion, creating the first atomic nuclei: hydrogen, helium, and a little lithium. This period is known as Big Bang nucleosynthesis. But the key turning point came about 380,000 years later, when the universe cooled to around 3,000 Kelvin. At that point, electrons and protons combined to form neutral hydrogen atoms. Suddenly, photons, particles of light, were free to travel without constantly scattering. That moment released what we now detect as the cosmic microwave background, or CMB. Discovered in 1965 by Penzias and Wilson, the cosmic microwave background, or CMB, is uniform radiation coming from every direction in space. It's the cooled remnant of the early universe, now at a temperature of just 2.7 Kelvin. That's only a few degrees above absolute zero, the coldest possible temperature, where all molecular motion stops. But the CMB isn't perfectly smooth. It contains tiny ripples in temperature, on the order of microkelvin. The prefix micro means 1/millionth, so 1 microkelvin is 1/millionth of a Kelvin. That's an unimaginably small variation, 0.000001 K, but those tiny hot and cold spots reflect differences in density in the early universe. Over billions of years, those fluctuations became the seeds of galaxies, clusters, and the large-scale structure of the cosmos. These faint whispers of heat tell us about conditions just 380,000 years after the Big Bang. The CMB is our oldest observable light, and it confirms that the early universe was hot, dense, and expanding. Most of the universe is invisible, not metaphorically, literally. The matter we can observe, stars, gas, planets, galaxies, adds up to only a small fraction of what's out there. The rest reveals itself only through its effects. Let's start with dark matter. It doesn't emit light, reflect it, or absorb it. No telescope can see it directly. But we know it's there, because of the way galaxies behave. In a typical spiral galaxy, stars farther from the center should orbit more slowly, just like planets in our solar system. That's what Newtonian mechanics predicts. But when astronomers measured those velocities, they found something strange. Stars far from the center move just as fast as the ones near the core. This only makes sense if there's a halo of invisible mass surrounding the galaxy, exerting extra gravitational pull. That's dark matter. We see similar effects in galaxy clusters. Light from background objects bends more than expected, a phenomenon called gravitational lensing. Once again, visible matter doesn't explain the gravity. Something unseen is shaping the universe. Then there's dark energy, an even deeper mystery. In the 1990s, two research teams were studying Type 1a supernovae, stellar explosions used as standard candles to measure distance. What they found was surprising. Distant galaxies weren't just receding, they were accelerating away. The universe's expansion isn't slowing down, it's speeding up. This suggests there's some kind of repulsive energy built into space itself, pushing galaxies apart. We call it dark energy, and right now, it's the leading explanation for the accelerating expansion. Here's what the current breakdown looks like. Dark energy, roughly 68% of the universe. Dark matter, about 27%. Ordinary matter, everything we've ever seen, just 5%. What is dark energy? That's still an open question. It could be a property of space, a cosmological constant, as Einstein once proposed. Or it might come from something dynamic and unfamiliar, a new kind of field, or even new physics. We're still working on it. But one thing is clear. Most of the universe is made of things we can't see, yet. Here's how redshift helps us calculate both the speed and distance of a galaxy. Imagine we detect light from a distant galaxy. We know that, when emitted, this light had a wavelength of 400 nanometers, right in the ultraviolet range. But by the time it reaches us, that same light has been stretched to 440 nanometers. To find the redshift, we use the formula Z equals wavelength observed minus wavelength emitted divided by wavelength emitted. That's Z equals 440 minus 400 all over 400, which is the same as 40 divided by 400, which equals 0.1. So the redshift is 0.1, meaning the wavelength has increased by 10% due to the expansion of space. To estimate the galaxy's recession speed, we use the approximation V equals C times Z, where V is velocity and C is the speed of light, about 300,000 kilometers per second. So, V equals 300,000 times 0.1, which equals 30,000 kilometers per second. This galaxy appears to be moving away from us at 30,000 kilometers per second. Now let's estimate its distance using Hubble's law, which says V equals h naught times d. we'll rearrange to solve for distance. D equals V divided by h naught, where h naught, the Hubble constant, is about 70 kilometers per second per megaparsec. So, D equals 30,000 divided by 70, which equals approximately 428.6 megaparsecs. 1 megaparsec equals about 3.26 million light-years. Multiplying that out, distance equals about 428.6 times 3.26 million equals about 1.4 billion light-years. So that single redshift value tells us this galaxy is not only moving away at 30,000 kilometers per second, it's also about 1.4 billion light-years away. And because of how long light takes to travel, we're seeing it as it was 1.4 billion years ago. This is why redshift is such a powerful tool. It's not just about motion, it's a direct window into distance and cosmic time. Misconception number 1. Redshift means galaxies are flying away like rockets. Truth: in most cases, redshift is due to expanding space, not motion through space. Misconception number 2. The Big Bang happened at a point in space. Truth: the Big Bang happened everywhere at once. It was space itself that expanded. Misconception number 3. We're at the center of expansion. Truth: every point in space sees galaxies receding, because space expands uniformly in all directions. Why does this matter? Our understanding of redshift, expansion, and dark energy shapes how we build telescopes, map the cosmos, and even calibrate technology. For example, the James Webb Space Telescope is optimized for infrared, because the most ancient light is highly redshifted. Without this knowledge, we wouldn't know how to look for the first galaxies. Even GPS satellites rely on relativistic time corrections tied to our understanding of gravity and expansion. The math behind the universe's growth affects the systems we use every day. If this helped connect the cosmic dots, give it a like or drop your questions in the comments. I answer them personally. And next time, we'll pull back the curtain on how we know all this. From spectroscopy to radio telescopes, to the secrets starlight carries. Get ready to see how astronomers decode the universe. The more we learn about the expanding universe, the more questions we uncover. Redshift, dark energy, the cosmic microwave background, each one is a clue in a story that's still unfolding. But none of this would mean much without the tools to measure it. Next time, we'll take a closer look at how we actually study the universe, how telescopes, spectrographs, and spacecraft help us turn faint signals into real knowledge. If you're curious about how we see the invisible, you won't want to miss it.